regression models. So here are the different terms we're going to go over today, some of which we have seen before. So a linear regression. So a linear regression, we're going to see what that is right now. But basically we can use, and throughout today, we're going to use the regression calculator to find a linear model. So like a model that displays that information, a graph for the data. And we're going to use the regression calculator to identify the linear regression equation. So what we're going to see here is we can use the regression model to find a linear model. So this is an example of the linear model that we have of that original data, but I want to show you how exactly we get this. So here I posted the regression calculator so you can access it. Let me move this over here so that I can see it. Okay, so how do I get that linear model? All I have to do is plug in the different variables that I have in the data set. This may seem like common sense, but I'm just going to show you. Two, 5, 4, and 12. And then because we have a linear regression, what we want to do is make sure we have the linear one selected, right? We'll look at quadratic and exponential today, but make sure you have that linear one selected. And what you recognize here is that you are given the linear regression equation, and you're also given the correlation coefficient right here. But what we're just looking at today is that equation. So using this regression calculator, we are given a model of how our data is plotted and that equation. And that's basically what you see here, all right? So basically you put every X and Y pair into the calculator, like you saw we did. And then after doing so, we get a regression model and an equation for that model. Okay? Give me 1 second. One second, guys. All right. Okay, so now we're going to use the regression calculator to find an exponential model. So this was a linear model. Now we're going to look for an exponential model. So to find the regression model for an exponential, you do the same thing. You just put each X and Y pair into the calculator, and you will see that we get an exponential model and the equation. So I will show you. And this time we do have to change this right here to exponential. So make sure you do that to get the right model. And then I'll go ahead and plug in each of our pairs. Five and 471. And there you see that we get our exponential regression model and we get our exponential equation, right? And that's what you see here, same equation. All right. So now what we're going to do is we're going to be able to make predictions with the graph of the model. So we're going to look at interpolation right now. And remember that interpolation is using or making predictions about things that exist within the range of data which were given. So here we're asked to predict the approximate number of bacteria colonies after 3.5 hours by evaluating F when X is 3.5. So as you can see here, actually you can't. Well, 3.5 would be located somewhere around here. And so because that exists in between, we have interpolation. So we can solve this problem by simply plugging in 3.5 into our exponential regression equation, right? And so let me show you what this would look like. It's not this class, okay. Make sure I'm sharing the right thing, okay. So we're asked to do interpolation, which is just make a prediction about data within the range of values given. So we're looking at 3.5, which is approximately right here. And we want to find the exact value for the number of bacteria colonies that we'll have after 3.5 hours. And so what you want to do is you want to look at the equation. The original equation is 10.18 times 2.15x. Okay, and so now we're going to plug in 3.5 for x. And when you do that, you can plug that into the calculator. And what you'll get is something that looks like this. Okay. Oh, nope, sorry, wrong one. Okay. And we're going to approximate that number to make it clearer. So I'll just do approximately 150 bacteria colonies. Okay, so basically what we're able to do here is once we have the equation for our exponential regression, what we can do is make a prediction by plugging in the value that we're looking for, in this case 3.5, into the equation and solve for, in this case, the number of bacteria colonies after 3.5. What we can also do is do extrapolation, which is making predictions outside of the range of data that we're given. So we have our original equation, and now we're looking to evaluate the number of bacteria colonies that there will be after 6 hours. So we're looking now for information outside the data set after 6 hours, so over here. And we'll see that we aren't given any clear indication of what that will look like after 6 hours, so we're doing extrapolation because we're working beyond the data set. But all we have to do is substitute x for 6, like we see here, and solve. And so we get 1,005 and 94, and I'll round that to 1,105. Okay, so using the regression equation, we're able to make predictions inside the range of the data that we're given and outside the range of the data we're given. Interpolation inside, extrapolation outside. Okay, any questions about this? All right, and now we're going to look at quadratic models. So we looked at linear, we looked at exponential, and now we're going to look at quadratic. And we're basically going to do the same thing. I did not mean to do that. Okay. We're going to use our regression calculator, and we're going to plug in this data to get, now we're working with quadratic, so we want to change this to quadratic. And then we'll plug in our information. So 0, -600, 100, -15, 200, 500, 300, 645, 400, 705, 500, 540, right? And so we plug in all of that information from our original data set. So we plugged all this in. And by doing so, we're able to get our resulting regression equation, right? And you'll see that we have the same equation right here. So that's the unique thing about a regression calculator, is it allows us to get information about the model. There's the model, and it allows us to get that regression equation. Okay, and we'll see that here. So you can do this for linear regressions, exponential regressions, and quadratic regressions. Okay, so now let me go back. Any questions about how to use the regression calculator? Questions? Concerns? Just plug in those X and Y's and make sure that you're on the right regression. Linear, quadratic, exponential. Okay. And so here's the difference between the two. Sometimes we may not be told exactly whether or not to create a linear regression or an exponential regression or quadratic regression. We have to determine which of them is the best fit depending on the type of data we have. So that being said, we have to consider the general shape and properties of the graphs of these functions. So we have linear. Linear functions have a constant rate of change. So the rate of change is constant, okay? Exponential functions, on the other hand, have a constant multiplicative rate of change. So basically things are being multiplied to it, where in linear things are being added. The rate of change is being added, and in exponential, the rate of change is being multiplied to it. So it moves faster, increases and decreases at a faster rate. And then the quadratic ones, quadratic functions do not have a constant rate of change, but they do have a turning point. And so if we have something that doesn't have a constant rate of change, it's not increasing or decreasing by a constant amount, then we know to use quadratic. So linear, if we have something that is a constant rate of change, it is moving a little bit slower, like it's adding 5 every hour or adding 10 every hour, then we'd know to use linear. If we're doing a quicker growing or quicker shrinking, so we're multiplying something by 10 an hour or 20 an hour, things are moving quicker, then we use an exponential. And then if we don't really have a clear rate of change, things are kind of just all over the place, then we would use quadratic, okay? We can also determine which type of function that we need depending on how the scattered plot is. So for example, we might start by putting information onto a graph in dot form, so like the orange dots. And then after that, we would create a line of best fit to better understand whether we have an exponential or a linear. And as you see here, it's kind of clear whether or not you have an exponential or a linear once you plug in those different data sets. Okay. So let's look at some examples where we're asked to find that rate of change, or asked to find which is the best fit. All right. So here we want to find the regression model. It says the total sales in millions of dollars for snowmobiles is given for the years shown in the table. Find the regression model that best models the data, round numerical values to the nearest tenth. Okay. And so what we see here is that we're not adding an exact amount each time, nor are we multiplying an exact amount each time, right? Our data kind of seems all over the place. There's no constant adding or subtracting of a specific value, and there's no constant multiplying or taking away from a specific value. So things kind of seem all over the place. And because things kind of seem all over the place, we might decide that we want to use the quadratic function and create a quadratic model. And so when we plug all this information into our regression calculator, let me show you. Okay. 4, 14, 15. Let's see where I am. Seven, 3, 9, 16, 5, 17. Basically, I'm just transferring that data set that I had into my calculator. And then 19, 4, 5. Okay, and then we saw we had a quadratic, right? Because we have no constant thing that's being added or subtracted or multiplied to it. It's kind of all over the place. And so therefore, we get our quadratic equation for this regression, which we see put right here as well. Okay? Any questions about this? We'll do one more example. Questions? No? And the reason we kind of know this is going all over the place is because if you see, here we're increasing in value, and then here we're decreasing in value. And so that change means that we don't really have a constant rate of change as we increase in years, right? Things are kind of all over the place. So now what about this? What do we notice here? Well, we might notice that things are decreasing, right? Things continue to decrease. They never increase and then decrease. And they seem to do so at a kind of a really fast rate, right? All of a sudden, from 0 years to 10 years, we have decreased about 21,000 in value, right? And so because of that, we might say that we have an exponential function. And so what you would do is you would plug in those values again, and I'm sure I don't have to show you again, but you would plug in those values. Because you have exponential, you want to change that. And this is the model that you would get, and here is the equation that you would get. Okay. Any questions? Okay, so finding and using a regression model. Okay, so you can see that the regression model or the linear regression model is the default. Notice that all the points on the scatter plot are far from the line. A linear model is not a good fit. Let's try a quadratic regression. Now this is a better fit than linear, however, there is no indication of turning point. So this may not be the best. Let's see if an exponential is better. The graph of the exponential model appears to go through all the points, so this is your best choice. Rewrite the function, running the values to the nearest tenth. And so that's kind of what you do here. What you want to do when you're asked to find the regression model is you want to identify which of those regressions is going to be best fit. Is it going to be linear? Is it going to be quadratic? Or is it going to be exponential? Okay. And then once we have decided what type of regression we're going to use, we want to find a model and our regression equation by plugging it into the regression calculator, plugging in that data we're given to the regression calculator. And then once again, linear functions have a constant additive rate of change, so they kind of increase or decrease at a very small constant rate. While exponential functions have a constant multiple rate of change, so they increase or decrease faster. They grow and shrink really quickly. And then quadratic functions are kind of all over the place. There's no indication of whether we're increasing or decreasing. Things are kind of all over the place. And so that's how we know we would use a quadratic. And then always consider limitations when making predictions using regression models. So we can make interpolation predictions about data within the range that we have, or extrapolation data from outside. And what you want to just make sure is that your data seems, or your resulting Y seems reasonable. Is it reasonable in the other one that we had 105 bacterial colonies? Yeah, it was. And so just keep an eye out for that. Make sure that your predictions are reasonable. Okay, any questions? And we'll go over some practice problems when we come back after spring break. Any questions? Okay.
No, ma'am.
There's no other. Okay. If there's no other questions, you guys may log off. Have a great spring break, and I will see you the following Tuesday. Okay. Bye, guys.
Bye, miss. Have a great day.
Bye. You too.
Bye, miss.
Bye.